In this video, we'll look into our first related rates problems. So this is the first application of the derivative. We want to see how different rates of change are related to each other. And so look at this example. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So let's draw a picture of what's going on. We have a spherical balloon and it's increasing. So V will be the volume of this balloon at time t. And we'll let R of t be the radius of the balloon at time t. So what we're given is that the volume of the balloon is changing at a constant rate of 100 cubic centimeters per second. When this is increasing, the rate at which the radius increases changes, because as the balloon gets larger and larger, you'll need more volume to increase the radius. Well, let's first write down the relation between the volume and the radius. The volume of a sphere is given by 4 over 3 pi times r cubed. But remember that volume and radius depend on time, and so the volume at time t is 4/3 pi times the radius at time t cubed. Now the question is asking how fast is the radius increasing? So what we want to know is the rate of change of the radius when the diameter is 50 centimeters. So let's first take the derivative of both sides. When you derive, on this side, this is just the derivative, dv dt. This side you have to use chain rule. Now we want to isolate dr dt, so we'll end up with something like this. dv dt divided by 4 pi r squared. When the diameter is 50 centimeters, then the radius is half of that. So the radius will be 25. So at the time of interest, r of t of 1, let's say, is 25. So we can replace that here. And we also know that dv dt is 100 at all time. And so plugging in, we'll get that this is 100 over 4 pi over 25 squared. We can simplify this so that the rate at which the radius is increasing is just 1 over 25 pi centimeters per second.